Okay, let's go ahead and get started. That's for later today. So keep an eye on your due dates. Number 2. I can't remember. Did I grade number 2? I vaguely remember grading it.
I'm pretty sure that you did grade number 2.
Okay, perfect. So,
yeah, number 3 was the one that is due
today. Yeah, okay, correct.
Yeah.
So we'll go over this one more time very quickly at the beginning of class, just because we're somewhat limited on time. I'll just go through the slides kind of quick. And then we have a new assignment number 4, that'll be due in 2 weeks. So now we're going to get into the part of the semester where we're generally doing an assignment about every 2 weeks. I know at the beginning of the semester it doesn't quite line up that way because I need to get some initial grades in for you so you know how you're doing in the course. But now we're getting into the point of the course where it's going to be like 10 to 15 questions, somewhere in that range, and then you have one of those due every couple weeks. Okay, so let's just get right into it. This is the chapter that we sort of started off with regarding understanding the various parts of the computer. And one of the things I usually like to do is we talked about the various parts of a computer. One of the things that I'd like to briefly talk about are hard drives. So there's 2 styles of storage devices. There are solid state, which have no moving parts, no motors or anything like that. And then these traditional, I always call them spinning hard drives just to remind you that it's spinning, but I think just the name hard disk drive, I think that sort of implies that. Normally I have a video to show, but since I'm broadcasting these lectures, I don't know if it's what the status of copyright and all that is, so I'm deciding not to. You're welcome to search for it. It's on YouTube. It's just, if you just type in hard drive in slow motion, it gives you a sense of exactly how fast these parts actually move. It's pretty interesting. And they just literally just show it full speed, and it's like you can't even really see what's going on, and they show you in slow motion, you see everything moving. So I would suggest later when you get home searching for that. It's pretty easy to find. Just search for hard drive slow motion. It's probably the first result on YouTube. But here's just a static picture of a hard drive. And I always like to think of it, even though it's kind of dated reference, as like a record player, is that you have these platters right here. They're basically magnetic discs, and they have microscopic little magnetic bits. And this spins around, and it actually has what are called tracks. You can't really see them here because this is a very shiny surface. It's like the shiniest mirror you've ever seen. But there's actual tracks. And what happens is that this arm right here, so there's a motor right here. This whole thing right here is called the arm. And then right at the edge, this head, that's what actually reads the data off of the disk. And so what has to happen is that if I want to read a piece of data over here, or let's say over here, what has to happen? So first, this arm has to move out here, and then it has to wait for this to spin around. So this is constantly spinning like a record player. I'm pretty sure it's a constant velocity. What happens if I want to read a piece of data here? It's not like I can reverse it. I have to wait for this to come all the way back around. Now these things are fast, but that's still like the difference between the speed of sound and the speed of light. You know what I mean? Like electrons in solid state devices move really, really, really fast. This moves fast, but it's not nearly the level. And in practice, it's not uncommon to get transfer speeds of like 3, 4, even 10 times the amount for higher end solid state drives. So the solid state drives are extremely fast. They're just a bunch of chips. There's nothing really interesting to see. It's like you open it up, it's a bunch of chips. This is a little bit more interesting because you actually see some parts moving. But anytime you've got moving parts, that implies a motor. And motors generally use more power, even though the motors on hard drives are actually pretty efficient. I always used to say that they used a lot of power, and I looked it up. They only use like single digits worth of power. They don't actually use that much, but still, they do generate noise, multiply that times 10,000 inside of a giant data center, and then you've got a lot of noise. And each one generates a little bit of heat, but again, you multiply that by 10,000. So, but this is just kind of a view of that, so you get a sense of how a hard disk drive actually works. Okay, but enough of that. So let's move on to and I think I covered everything that we wanted to essentially here. So then we moved on to the internet or / networking chapter. We actually have two that are like this. Assignment number 3 is based off of this. So again, like last time, I suggested that you have a Word document open. And I think we basically covered all these, but let's just kind of hit the main points here. I'll be done through this in about 15 minutes. That way we can move on to new material. Okay, so the informal definition that I kind of like, and I think it's a pretty decent definition of the internet, is just it's a network of networks. So you might think, okay, well, what is a network? Remember we went through that whole thought process, and I'll do it very quickly, but if I've got 2 computers in a room and I've got a bunch of data, well, I could put that data on a flash drive, pull out the flash drive, put it on the other computer, or I could put a cable in between them, and then those computers can talk to each other. We'll get into what I mean by talking in a little while. Then you want to add a third computer. Okay, you can do that. And eventually you end up with a classroom full of computers, and you put them all together in a device called a switch. Well, what if I wanted to communicate with the classroom next door? Well, I could connect the switches, and then I could do the same thing for the whole building. And then they would all usually go into a device maybe called like a router, or they have very sophisticated switches these days, so it might just be another switch. And then same thing, you want to get all the buildings on campus together, and then so you connect all those together, and then so on and so on and so on, until essentially you have the whole country networked together, to where if I wanted to send a data packet from here all the way out to Seattle, Washington, it knows how to find a path going from here to what's called a internet backbone, so maybe in like somewhere South Florida, maybe Miami. And then from Miami, they have these giant, what are called backbones, giant internet connections that might go from there to like, it's tough to say, maybe Atlanta, probably a few hops through the Midwest, maybe Chicago or something like that. And then eventually it gets all the way out there. So that's what the internet is. It's you take all these small networks and you keep on connecting them until eventually you have this giant network where any computer can theoretically talk to any computer. We have security reasons why you wouldn't do that, but theoretically, if you removed all the security, you could. And I already mentioned I don't like this second bullet point, the secure form of communications. By default, none of this stuff is encrypted or secure in any form. The original scope of the internet, it was actually called ARPANET. So the organization that created all this was called DARPA, Defense Advanced Research Projects Agency, and they created a network called ARPANET. The original ARPANET was essentially military, government, and universities. And I'm not going to show it today, but remember last class I showed you the map of the internet in 1977 or something like that? That's how small it was, that you could actually put it on a piece of paper, and it grew since then. Now don't get the internet and the web confused. Web is actually built on top of that. The web actually appeared in the early 90s, and we'll eventually get to that. But the internet is these things are layered into what's called OSI layers. The internet would be the lowest layer. What we call a TCP/IP network, that would be the lowest layer. The web is built on top of that. We'll get into network architectures a little bit more later, but the main two that are most common today are peer-to-peer and client-server. Peer-to-peer is generally easier for people to understand because it's literally if you took every single computer in this room and hooked them all together and said, okay, I want a piece of data from this computer, I want a piece of data from this computer, they all talk to each other. Now, because you sort of lose control with a peer-to-peer network, and it can be very difficult to keep things in sync. So they tend actually not to be very popular, but they're very resilient. In that sense, you've got 30 computers in this peer-to-peer network. some number of those computers can break or go down, and the network essentially still runs. It's most popular with file sharing services, like if you're sharing a piece of music that you made or something like that. It's very easy to distribute because once you've made that piece of music, the chances of it changing are not that great. But for, like, say, a document that's always changing, like, I don't know a good example, but most documents actually change all the time. That's probably not a great thing to do because you have really no central control. Client server, you tend to have much more central control. And so you've got this one server. In practice these days, they came up with many ways to make many servers appear as one single server. And it's great because you have centralized control. If you want to change something, you just go on that server and you can update a file. But it's not as resilient because if there's any issue with that server, then, for example, if the server in question is www.irsc.edu, if that server goes down, nobody can visit that website. Now, like I said, in practice, this is an oversimplification because we've come up with very, very clever ways of a single server, quote unquote, actually being many, many servers all across the country. So it's a little bit of an oversimplification. So we use what's called TCP/IP as the main protocol for the internet. So let's take a step back. What's a protocol? In this classroom, the protocol is English. You walked into this classroom just sort of assuming ahead of time that I was going to speak English, and you go into that knowing that, and then you understand what I'm saying. We're able to speak to each other. Computers are the same way. They need some common language, but their language is much, 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 much more formal in that if I'm having a conversation with somebody, I can interrupt them, or they can interrupt me, or we can try to talk over each other, and it's a very informal way, and then somebody can go on for too long, and with computers, you can't have that. You have to have very specific, okay, you're allowed to talk for this amount of time. You're going to send me this information. From there, I'm going to process it on my end, and you end up with this very formal of who can talk exactly when, for how long, and what information should be provided. So that's what's called a protocol. And you've probably seen these just in life. They're not specific to computers. Maybe at your jobs you've had a certain protocol. Like, for example, if a customer returns an item, you might have a specific protocol to process that returned item. Same thing here. It's just essentially a set of steps to keep things moving. So the internet, we say TCP/IP is the protocol of the internet. And that's really built upon. And if I'm communicating, well, if I try to call somebody on the phone, what do I need? I need a telephone number. If I want to mail somebody a letter, what do I need? Their home address. Same thing here, that if I want to talk to another computer, I need its internet protocol address. And we went through the exercise last time where we opened up a command prompt and we actually looked at our own. And that's actually a part of the assignment, so we don't really have time to go through that process again, but it's recorded so you can go to last week's lecture. But that's what we have, is these IP addresses so that we can all talk to each other. Some of the ordering of this stuff is a little bit awkward. Let's skip around a little bit. So let's talk about this thing right here, this www.newyorktimes.com. This is what's called a domain name. Why do we have a domain name? Why don't I just type in an IP address? Well, let's take a step back. Computers and other mechanical equipment tends to work best with numbers. We've already seen this with phone numbers. Same thing with the post office likes to use zip codes. Numeric systems work really well because you can organize them certain ways. You can say this range of numbers corresponds to this range of numbers means something else. This range of numbers may belong to a specific company and they're allowed to have all the numbers in between. So we can do a lot of organization with numbers. The other thing is that computers are very fast at processing numbers, so we get organization and speed. Are people good with numbers? Not generally. What do most of you do in your phones? Do you memorize all the phone numbers of your friends and family? Generally not. What do you do? keep contacts. What's that?
Oh, like put a name on it.
Exactly, yeah, you attach a name to it. And even though there's no real formal name for that, you just might call that your contacts list. It's kind of the same thing, is that you work with names very well. You might say, okay, this is Alice, and this is her telephone number. And rather than memorizing the phone number, you just look up Alice, and then when it dials the telephone number for you, but you've retrieved by name. We sort of had the same thing here, is that computers work really well with numbers. We work well with names. So we have this system called DNS, Domain Name System, that does that for us. And when we have these DNS servers where we actually do this mapping, where we say, okay, I'm the owner of NewYorkTimes.com. I want to add a subdomain, www.newyorktimes.com, and I'm going to attach it to this IP address. I did mention that we can go the other direction. The other direction gets a little bit complicated because, like I said, a lot of times we don't have a single server anymore. So it gets a little bit more complicated. But reverse DNS can be useful, but 99% of the time you're just going to be using regular DNS of going from a name to a number. And then once it's a number, computers and networking equipment are really good working with numbers. So let's talk about the web very briefly. So as I already mentioned, we have these things called OSI layers. And at the lowest layer are the protocols that do the base communications. So what I mean is, like, we deal with packets. And if I send you a packet, sometimes they may arrive out of order. Sometimes they might be too old. Sometimes I may get duplicate packets. And within that is the actual little chunks of data. And no matter what I'm dealing with, whether it's email, the web, or any chat, it doesn't really matter these low-level details so much. I just need to get data from point A to point B in the correct order, and I need guaranteed delivery. And that's what TCP does. So once we had that in the, let's just do a decade, let's say the 70s, then people were able to start building things on top of that. Email, chat services, and so on. And they didn't have to worry about these low-level details. They just said, okay, I have a message that says good morning, and I want to send it to this user. And so over this chat protocol, it is able to use TCP to make sure that that message gets over to that other user. Now, in the 80s, we had a few of these. We had email, which is SMTP, Simple Mail Transfer Protocol. There's one for chat. It's called IRC, Internet Relay Chat. I want to say IRCC. IRC. There's many others. And then in the late 80s to early 90s, a guy named Tim Berners-Lee came up with the idea for the web, the World Wide Web. And that was basically just a bunch of documents using this language he created called HTML. And the documents could have links to each other, hyperlinks. And we don't even think twice about it today. When you go to a website, it's going to have links everywhere, and we wouldn't call it a document, we would just call it a web page. If you go to the IRC website, within 30 seconds of being on the website, you could probably click a dozen links and end up all different places on the website. But that wasn't actually very common back then. It used to be more like, imagine navigating a PDF, where you might, if you're lucky, you get a working table of contents, but you have to scroll through and find different pages and so forth. Imagine the IRC website if they just gave you one giant PDF versus something that you can navigate and click through. So he created this in the early 90s and created a very early browser. Those early efforts eventually became a browser called Netscape. And Microsoft, very early on, realized that the web was going to be huge. They haven't always done things right. They've kind of had a few directions that they went down that never went anywhere. They never really quite got a huge mobile phone following. Even their music players, I don't know if anybody remembers the Zune. But one of the things that they did do right was realize that the web was going to be big. And so what they did was, Microsoft was competing with a lot of different companies at the time that aren't really, I don't want to say they're not around, they generally got bought out. Companies like Sun Microsystems was a large one. IBM had a lot of Unix systems, HP. And so it was a very competitive marketplace, and so what they tried to do generally was lock people into their platform. So you've got this very open web browser called Netscape Navigator, which cost $30 or whatever it was. Let's just say 30. And so what they did is they came up with their own web browser that they gave people for free. Now, what are you going to do? Are you going to pay $30 for a web browser, or are you going to just use the free browser provided by Microsoft? And so most people use the free browser. What they did was they started to put Microsoft-specific extensions. One of the things was that the web was supposed to be open, that anybody from any computer, as long as it had a standards-based web browser, could connect to it. And what Microsoft decided to do was, let's make a non-standard web browser. That way, people start making websites that are specific to Internet Explorer. And, well, that didn't end super well. There was a whole antitrust case in the late 90s. And unfortunately, what ended up happening out of that is that Netscape went out of business. They open sourced all that code, which eventually became, through a very long path, eventually that became Firefox. So Firefox has its roots all the way back to the early days of browsers. Who knows how much original code is left? Because every once in a while you go through this process of refactoring where you may rewrite and get rid of older code. Microsoft Edge has its roots back to Internet Explorer, sort of. Microsoft Edge was supposed to be a complete rewrite of the browser, and now they actually have a new version of Edge. I don't know if anybody's seen it. I checked it out a few months ago. It's actually based on Google Chrome. And so I'm sort of thinking that the era of Microsoft-based web browsers is kind of coming to an end. I think they're just going to base their browser on the insides and the internals and the guts of Google Chrome, and they're just basically putting their own user interface on top of that. So that's Firefox, Microsoft Edge. Now, where did Google Chrome appear? Well, in the late 90s, early 2000s, Google got their start for search engines. And search engines by itself don't really make money. People assume that it's going to just be like a free service. So very early on, they realized that what they could do is inside these search results, they could insert ads. Now, and the search engines before Google were pretty terrible. A lot of them, they would just have groups of people going out on the web and saying, okay, this is an interesting link, this is an interesting link. It was very much human-powered. They did have these things called crawlers, but the algorithms that they used were very, very simplistic. And Google came up with an algorithm called PageRank, which is based on, anyway. But they came up with a very clever algorithm. Well, they knew that if Microsoft had complete control of the web, that would really hinder their business model because they were really betting big on the web. And they weren't really a desktop applications company. They weren't really an operating systems at the time creator. They were mostly putting all their whole business, they were betting large on the web. And so what they realized is that for the web to succeed, we can't always be dependent on Microsoft because at any time they could decide to break all of our websites. And they've done it in the past. They saw that they already had killed Netscape. Netscape after that really essentially didn't exist as a company anymore. So what they did is they came up with their own web browser. And it's actually very amazing how quickly Chrome became popular. It's relatively new in computing history. Out of all the browsers listed, it's the newest, but I think if you look at, maybe we'll do this today, if you looked at the different market share of the browsers, I think it has the highest market share, which is interesting because Microsoft Edge comes with the operating system, so you actually have to go to extra effort to download and install Chrome, and still people tend to choose it. Just out of curiosity, quick survey, how many people use Chrome? Yeah, that's usually pretty much the breakout of it. And lastly, Safari. Safari's got a kind of a weird, not weird, but it's I think it was awkward for Apple to have an operating system, the Mac OS X, and not have their own web browser. So I think that's really where Safari came about, is that they could have probably just used somebody else's web browser like Firefox and made improvements, but I think it was just kind of an awkward thing to be like, oh, we've got this amazing operating system and no web browser for it. So they based it off of a very old browser now called, I think it was called Conqueror for something called KDE, and it used WebKit and KHTML. But I think that was so long ago. I'm guessing it probably has very little in common anymore. Okay, but those are the main web browsers. Now, when I go to a website, I have this thing called a URL, Uniform Resource Locator. And here's the breakout of it, is that in blue, I have this thing called the protocol. And originally, I think they had the idea that there were going to be more protocols. Sorry, I like to check every once in a while, make sure I didn't actually drop any, okay, not dropping frames, perfect. I just had incidents in the past where half the lecture wasn't recorded, so I just have to be careful. Most of the time, we're going to be using HTTP, HTTPS. There are other protocols, like maybe you've had like FTP, and there are other protocols, but the bulk of the time, you're going to be using one of those two. And it's a very long story, but how many people have heard the name Edward Snowden before? Okay, so he was a contractor for the government, and he released a huge set of documents. It's a very, very long, complicated story. I'm over summarizing here, but basically there were documents showing that there were programs watching unencrypted traffic, and it looked really, really bad on these large companies like Google and Microsoft and Apple. And so what they all kind of collectively did is said, okay, when all the traffic is unencrypted, essentially anybody can look at it. Now, at that time, very important stuff was encrypted, like your banking information, but kind of relatively mundane things weren't. And so all these large tech companies came up collectively with this idea that let's just make all web traffic encrypted. And so that's why these days you're seeing more and more HTTPS. The S stands for secure, but really you can think of it as encrypted traffic. And encrypted traffic, it's just essentially scrambled, where you can't really see the original data that's being passed back and forth. And actually, even in modern browsers, I think Chrome, they actually warn you now, it's flipped. If the website is not encrypted, even if it's something very mundane, like a recipe or something like that, on a, that you don't care if somebody sniffed your traffic, I think it'll still give you like some sort of indication that it's unencrypted. That, by the way, happened very, very, very quickly. It was like almost overnight. And it used to be, you had to pay for these things called SSL certificates. And now there's this big project that they helped. Many of these, it's not just one tech company, it's a bunch of them. It's called Let's Encrypt. And it used to be you'd have to pay like $30 a year for one of these certificates. Now it's incredibly easy. I remember how much work we used to have to do to get these SSL certs. The company would actually have to call you, and you would have to verify that you're actual real person, saying that now it's a completely automated process, and you don't generally have to pay money for it anymore. We already talked about the domain name. Now, when you go to a website, the website's on a server, and the server file systems are kind of the same on your regular Windows computer. You're going to have files and folders. When you go to a page on that website, their website's typically organized into files and folders. And that's this orange thing at the end, the path and subdirectory. That's just basically the directions to get to that file that you're trying to get to. So in this case, it's a folder called pages, and then either a file or folder called technology. Now, in reality, these days, I'm always careful of how I say things, because people in tech always come up with very clever ways of making it appear something is and it isn't. Modern web pages, actually, or websites, there's not a lot of actual physical web pages anymore. A lot of it is generated content from programming languages, but anyway. Let's very, very briefly talk about what a search engine is, and then I want to move on. I think that kind of covers everything I want to. Okay, so a search engine, so let's go back to the early days of the web. The web exploded. It was what's called exponential growth. Imagine doubling the number of websites every month or something like that. If anybody's ever seen like a video of bacteria growing or dividing, like you look a few hours later and you've got thousands and thousands of bacteria. It's kind of the same way. It's what's called exponential growth. And that's what happened with the web. It just kept on getting larger and larger and larger, and it was just very quickly, it went from thousands of pages to millions to billions to, it wouldn't surprise me if now we're in the trillions. It's way too big for any one person or any people in general to organize that and to curate that and to like and it's been so long I can't even remember the name of them anymore. People actually used to do that. They would have these websites where that's all they did is they said, oh, okay, if you want to know about cats, here's all the different websites about cats. And it was very impractical. So very early on we realized that, okay, we have to have an automated system for doing this. Now, a very simplistic system is that, okay, if somebody types in the search engine cats, go out to the web, crawl all the web pages about cats. Well, it gets kind of complicated because if somebody wants to, say for example, create a web page that shows up at the top of that search result, maybe they could have a banner ad at the top where they made money every time somebody visited the page and just write the word cats 50 million times. And so, okay, we have to start controlling for other things. And what happens if when the search engine hits my page, it's for cats, but then it returns something else, something where I make a lot more money. Let's say, for example, if I'm selling insurance. So somebody's searching for cats, the search engine sees, okay, here's cats, I'm going to send you to this page, but then the page I return is actually selling insurance. So it's a very, very complicated process. Google came up with, if anybody's ever interested, it's an algorithm called PageRank, and it solved a lot of these problems back then. People eventually started to kind of game or hack PageRank, and then now they have much, much more sophisticated algorithms. They're not as open about their search algorithms as they used to be. But I read an article a few years ago that in a single Google search, it's not uncommon for that search to pass through 150 algorithms. So, but the basic idea of a search engine is that you type in some sort of keywords or a phrase, and it does its best to try to find results. This field, by the way, it's called natural language processing, and text retrieval. There's a few associated fields. Information searching, information retrieval. So it's a whole field of research. Google still tends to be the leader in it. And now we're actually getting even more sophisticated. If you've maybe noticed in the past few years that it's actually a question and answer system. So if you asked it a very factual question, like what's the capital of Florida, if anybody wants to Google that real quick and see it, I'm guessing it probably would come up with the correct result. So it doesn't even send you to a web page with the correct result anymore. Typically with these natural language processing systems, they're so good now they can actually just give you the direct result. So this is kind of an older technique. This will be the last thing on this chapter. Maybe some of you have seen this at libraries. We don't tend to use these anymore. They were called Boolean searches. Has anybody experienced this at like a library where you have to write, if you're searching for a book on, say, the history of Florida, you'd have to write history and Florida and 1800 or something like that. They were called Boolean searches. They're not very user friendly, and they're just not very sophisticated. We don't tend to see these almost anymore. We just sort of trust that Google's $1 billion of research that they put into information retrieval and search engines is probably better than some handcrafted Boolean search that I could come up with. Okay, I think that's pretty much it. Let me just make sure I talked about everything. So we covered what is the internet, covered this. We did this last class, so you can look at the video from last class. We talked about this last class. We talked about this class DNS. What's the purpose? Same thing with IP addresses. We just gave an example of URL earlier. This is a research question. We talked about this class. This is a research question, and we just talked about this a minute ago. Okay, so any questions on anything? Everyone should be done or very close to done? How many people are done or very close to done? Show of hands. Okay, just make sure to get it submitted. And that's all I want to do with that. What chapter was that? That was 3. Okay. Okay. This one I might go through kind of quickly. Actually, I want to do some things out of order. We'll come back to this. I'm just going to jump right into 5. I want to make sure we get through everything this semester. Some of these chapters aren't that interesting. It's like, what is application software? Some are actually way more interesting, like the stuff about networking and operating system software. So many of you will end up in some sort of career in IT, and system and operating system software is where you're going to spend the bulk of your time, managing these systems, doing things like finding IP addresses, changing IP addresses, setting up to print to printers, a lot of administrative tasks, those sorts of things. So most of you probably aren't going to spend most of your day using like application level software, say like Photoshop or something like that. Most of you will spend your day in system software. Okay, so this corresponds to assignment number 4. Okay, so let's very quickly read over these. So find a chart of the market share for desktop and mobile operating systems. Turns out they're different. We're going to talk about Unix, and there's something called the Unix family tree. Microsoft at one point actually made a Unix-based system. We'll talk about what Unix is in a little while, but this is a research question. We're going to talk about system software versus application software and drivers. And what will often happen is, has anybody in here ever gotten a bad driver? Usually it's video card related, sometimes motherboard. Show of hands, anybody happen to? And then what happened with the was it a bad driver? Okay, yeah. And so what happens often in time with these drivers is that they'll crash the whole computer. Versus if you download an app or something that's just kind of not really well written, the entire system doesn't crash. Usually just that app crashes. And we'll talk about why in a little while. We'll talk about the BIOS. This is kind of a research question. I should have marked it that. Common file systems. We'll talk about file systems, interrupts, the entire purpose of an operating system, back to file extension stuff, and then graphical interfaces and command line interfaces. Okay. So this chapter is on operating systems, and you'll actually have to take 2 classes on operating systems. You take I think a fundamentals class and then a Unix Linux class. And let's take a step back. Let's not just start using terms without defining them. What is an operating system? So I always like to go back all the way to World War II era computers, like Cold War era, the stuff from like the 50s and maybe early 60s. Very often, those computers were just fancy calculators. I would feed it a program. It's a style of processing called batch processing. So I would take a card, they're actually written on punch cards or some sort of other magnetic disk. I would put it in the computer. That program would run, and then many hours later I would get an answer. This is the most common way to run programs. And that was great because it replaced a whole room full of people doing this process manually. And that worked great. But what they realized is, okay, these computers are starting to get complicated. So there might be, and just to take a step back, this is not necessarily true of modern computers, but computers back then, and up until maybe like 10 years ago, they actually only run one program at a time. So when I start a program, it just runs one program at a time. But you might think, well, that's weird because even 10 years ago, I would have multiple windows and multiple programs running at the same time as my computer. What happens is that we can slice these programs up into tiny little slices. And so we can say is run this program for 30 milliseconds, run this program for 10 milliseconds, run this program for 15 milliseconds. And what happens is that when you do that round robin, it sort of looks like the computer's actually running 10 or 20 programs. Does that make sense to everybody? If you take tiny little slices and let each program run for just a tiny little slice, it seems like we've got a bunch of programs running at the same time. So we talked about in the first class about this idea of a bottleneck. So let's think we've got CPU, we've got RAM, and we've got some sort of storage. CPU is really, really, really fast. But CPU can only process data as fast as it gets it. Remember our hard drive? Remember we had this spinning thing that sort of looks like a record player? And then I need a piece of data that's way over here. What do I have to do? I have to wait for it to go all the way back around and get that piece of data. That might take 10 or 15 milliseconds. What's happening in that time? The computer's doing nothing. It's just sitting, the CPU sitting there, said, I asked for a piece of data. I'm waiting for that data. I'm just sitting here doing nothing. Imagine if the early computers that you could only run one program, not one program at a time, just one program. You'd run it until it finished, and then that was it. If I've got this computer that's tens of millions or hundreds of millions of dollars, and I'm just sitting there spending most of the time waiting, so the CPU asks for a piece. Remember, the CPUs run in, back then, thousands or millions of operations per second, but today they operate in billions with a B of operations per second. So I've got this very, very, very fast thing called the CPU, and this very slow thing called my hard drive. And the hard drive has to feed data to the CPU for it to do anything. Now, one thing I could do is, okay, and so if I've got a multi-million-dollar computer and it's sitting, the CPU is sitting idle most of the time, I might think, well, rather than just running one program, can I come up with a clever way of running two programs? So what that means is that when the first program starts waiting for data from the hard drive, I can switch over to a second program. Does that make sense to everyone? So I've got a program running, and the hard drive says, okay, I got to find this data. It's going to take me, let's use a round number, 100 milliseconds. Are we going to just waste a tenth of a second of the CPU doing nothing on this $100 million computer? Or can we start to run a second program for 100 milliseconds and kind of start to fill in those gaps? What about a third program and a fourth program? So the whole idea of an operating system is that we can start to do multiple things at the same time on that computer. That way, where the computer might be active for, say, 10% of the time, it would just spend most of the day doing nothing, and then short bursts of calculations, and then sit there waiting again and waiting and waiting. Now what we can do is we can start to fill in those gaps with other programs. But we have to start it, as soon as we do that, it gets very complicated, because we might say, okay, in this process of switching programs, it's called context switching. And you might say, okay, well, the first program might get a certain amount of time, and the second program, how do we decide who's more important? Well, one way might be to evenly slice up the programs. One way might be to decide, okay, do it only when the program is waiting. And there's a whole field about operating system research. But the system that allows us to run multiple programs on that computer and to switch them and go through this process of switching. Because remember, we can only run one program at a time on the computer. But this thing that goes through and switches very quickly, this is called the operating system. So the operating system goes all the way back to probably about the 60s. And it's this idea that we want to make better use of our hardware by running multiple programs at the same time. And that's really the main reason that we have operating systems, is that so we can do what's called time sharing. You don't tend to see this term very often anymore, but there was actually computer systems where it was called time sharing systems, and you would have to pay for those little slices of time. That's not generally how you're billed anymore, but Um, there were some very early research operating systems, but really the most common operating systems in usage today. So there's kind of two families. So in the late 60s, early 70s, there was a failed project called Multics. And it was, I don't want to say it was completely failed. It just never really, I think, it was over budget, took too long. It was this gigantic project. And there were some programmers from AT&T, back then it was called Bell Labs, who were working on this project, and they said, well, let's come up with a slimmed down version. We don't want this multi-million or multi-tens of million dollar projects with hundreds of programmers. Let's create a very slimmed down version. And so they created a slimmed down version called Unix. And it was almost immediately popular. It used the same principles as this Multics system, but it was a very slimmed down version. It was called Unix. And very quickly, AT&T and other companies saw that, oh, this is amazing. Because at the time, the operating systems were very, very, very clunky, but this was a very, for the time, smooth operating system that was very consistent. It just had a lot of good qualities about it. Well, at the time, AT&T was all about making money. I'm sure they still are. And so what they realized is that they could start to license the source code and let other companies create variants of this. And they were in with the universities as well, so they would give the source code to the universities. So we saw this explosion of Unix variants and clones. And a lot of times we use the term Unix, but often we mean some sort of Unix variant or clone. And that's what this link is right here. So going all the way back to 1969, this unnamed PDP-7 is just a computer that was popular at the time, Unix operating system. And you can see as they started to license and give away the source code, more and more variants of this Unix operating system started to appear. And some went away and you never really saw them again. I'm trying to find some here that went away. Unixware I don't think is around anymore. AIX I think is still kind of around, but I don't know how often it's used anymore. But we see going all the way back to this operating system from 1970. Let's scroll to the bottom and let's look at what we see today. So some of these I don't expect you to know, but some of them I expect you to know. So of these operating systems on the bottom row, can you name any that you recognize today as common operating systems?
Mac OS.
Exactly. So the most obvious should be Mac OS. So Mac OS actually has its roots all the way back to the original Unix operating system. Any others that maybe some of you have heard of? Linux. Linux has, even though it's what's called a Unix variant or clone, or it's notice that it doesn't have a direct, like you can't follow a line all the way back up here. What they did is they said, let's make an operating system that's kind of like Unix, but for most purposes, most people just consider it close enough to Unix that it's just Unix. You can get into very low level details, but so these two are very common. Now some of these others are still actively maintained, but you might not see them that much. Minix is a research operating system, so if you go to certain universities and you're taking an operating systems class, you might study this. FreeBSD is kind of more on the server side. I want to say, I don't know if this is true or not, I got to research this later, but I heard that Netflix uses a lot of FreeBSD. I don't know if that's still true anymore. OpenBSD is meant to be very security oriented. But this is interesting because, okay, so I'm telling you that there's two basic families of operating systems. There's Windows, which we'll get into in a second, and there's these Unix-based operating systems. Already we're seeing two right here that are in common usage today. If we were to extend this chart out a little bit further, what mobile operating system is based off of Linux? Android, exactly. So it's not listed here, but Android, if you were to extend this out a little bit, you could actually see that Android is actually a Unix-based operating system. Now, OS X is the desktop operating system, but the same applies to their mobile version, is that it's essentially the same internal systems. And so even iOS is really considered a Unix-based operating system. So even though we've got these many operating systems, we really actually, for general purpose operating systems, we really only have two families. We have the Windows family and the Unix family. Let's quickly talk about the Windows family of operating systems. And that's why you can see here, even though they have a bunch of operating systems listed here, of those, how many are Unix-based? So we've got 5 operating systems listed. How many are Unix-based? 4 of the 5, correct? So even though they're listed as different operating systems, they really have the same roots. Now, we see one here, Windows, that's completely different. Windows has an interesting history. In the 80s, they would create what were called Unix clones, and these things were everywhere. You saw in the chart there were dozens and dozens of these Unix clones. And Microsoft was smart, and they said, we're never going to be able to compete with these Unix clones. There's just way too many of them. And it was big companies too. IBM, HP, Sun, just so many of these that very large companies. They're like, if we try to compete, we're just going to become another Unix clone. And by the way, what happened to all these companies? Pretty much none of those Unix clones exist today. It's almost across the board. It's Mac OS, Linux, and BSD variants. That would account for probably 99% of the Unix out there. And so Microsoft was smart. They said, let's come up with the most different operating system that we can, and let's market it for home users and make it as simple as possible to be used. So we're not going to care about the corporate environment. We're not going to any of that. Let's try to make this an easy operating system for home users. And that's where Windows came about. And their general philosophy was that when home users start to use their operating system, they're going to get to work. And what are they going to use? They're not going to want to use this weird Unix operating system that they don't know how to use. They're going to want to use the same computers that they use at home. And then eventually what happened is that's when you started to see Windows take over the corporate environment as well. But that's essentially what happened with Windows is Microsoft said, we're not going to win this Unix battle. Let's do our own thing completely. And obviously it worked out well for them. So we really have kind of 2 branches of operating systems. We have Windows and Unix-based operating systems. Now, one very interesting thing, Microsoft for a very short time did create a Unix-based operating system, and they just kind of very quickly abandoned it. I think it was clear it wasn't in their best interest. It wasn't going to make them a lot of money, and so it wasn't around very long. Okay, so a little bit more, and then I'll give you some time to fill in so let's say 5 more minutes, and then I'll give you some time, last 15 minutes of class, to kind of fill in some stuff for your assignment. Now, we have different types of operating systems. We have general purpose, we have real-time operating systems, we have server operating systems, and so usually what happens is that you want to make an operating system that's kind of geared toward its task. So Android and iOS, because these devices run on batteries, you want it to be a battery efficient operating system. And so that's why they create separate, they don't just use a general operating system that you would also use on your desktop. They try to come up with a system that doesn't use a lot of battery. You have slightly different user interfaces. You have touch user interfaces versus on a desktop, you're going to have a mouse and keyboard. So even though much of the internals of the system is the same, they try to make it user-friendly. So that's why we have these different mobile-based operating systems like Android and iOS. Linux tends to be used on servers a lot, even though I personally use it on the desktop. The place you're going to most often find it is in data centers running on servers. Mac OS, that's generally geared toward a desktop operating system. And then Windows is kind of both. You can run it as a server operating system or a desktop operating system. There was a period where Microsoft was making very large investments to try to make it a mobile operating system, but I think in 2020 by now, I think they've essentially given up. I don't think they're putting a whole lot of effort into it. 5 or 10 years ago, it was a different story. They were putting a bunch of money into it, but I don't think so much anymore. So let's very briefly talk about market share. So on the desktop, by far, and by a very large margin, Windows is going to be the most used operating system. It's by a lot. It's something like 85 to 90%. I could put a pie chart out as an announcement, but it's the huge majority is going to be on Windows. And then Mac OS on the desktop and laptop, it has some share, and then Linux has a little bit. But on the desktop, the bulk is going to be Windows. On mobile, it's actually completely opposite. It's flipped. Like I said before, very few people are running Windows on mobile anymore, even though they had some phones for a while and they were pushing it for a while. I think they've essentially given up. I haven't looked at the stats in about a year. When I last checked, Android had the largest market share. I'm guessing it probably hasn't changed much. And then iOS. I don't think Apple actually cares that much because Android's a different ecosystem. So the way iOS works is that Apple creates Apple-branded phones. They create the hardware. They create the operating system. All profits go directly to them. Android's typically associated with Google. Google doesn't make all the hardware. Motorola makes phones. LG, yeah.
Well, Google does make the Pixel phones.
Correct. Yeah, yeah, you're right. Yeah, so they make Pixel phones, but they don't. It's very spread out. There's probably, let's say, 30 to 50 companies making Android phones versus Apple is kind of like the sole. So it's a little bit more difficult to kind of compare the two. It's a little bit different of an ecosystem. So, but in general, if you just looked at mobile operating system share itself, Android tends to be the highest. And then web-based Chrome, I'm not going to get into that. Not that interesting. Okay. So we'll end on this slide. This is just as a quick summary. Remember, going back to the very early days of computers, is that we could only run one program and it would run from start to finish. And that was great, but then we realized that most of the time the computer wasn't utilized. It would spend a lot of time waiting for input from the user or waiting for the hard drive. It just spent a lot of time waiting. So they said, okay, let's come up with a system where we can actually run two programs. The first program runs until it has to wait, and then we say, okay, it's waiting on something, let's start to run another program, and then add more programs, and eventually that led to what's now called the operating system. It manages all that. Now, when you're running programs, multiple programs at the same time, it actually gets kind of complicated because there's more to that. If you're running multiple programs at the same time, two programs can't write to the same file at the same time, so it gets kind of complicated there. You have to worry about if it tries to access, like, say, a printer. And this is generally a good way of thinking about it. The operating system kind of orchestrates everything. It orchestrates the hardware, security, file permissions, who can read and write to the hard drive when, and so forth. Okay, and that's the whole reason that we need an operating system. If we only ran one program from start to finish, we actually wouldn't need an operating system. It wouldn't really make a whole lot of sense. It really only starts to make sense when you're running multiple programs at the same time. Okay, so I think that's a good stopping point. Go ahead and make some progress on the assignment today. So let's see how much we got through today. Okay, so this is kind of a research question. We talked about it, but you can Google it. We talked about this. This is research. We talked about, I didn't name the operating system, but it's very easy to find. And we didn't talk about this. We talked about number 8. And that's it. Okay, so you should be able to fill in about a third of the questions to half, somewhere in there. Okay, any questions on anything before I stop recording?